Next, we will explain the optimization of a deep drawing process. This particular industrial case was presented as Benchmark3 at the NAMISHIT 2011 Congress that took place at South Korea. It was optimized through 13 design variables and 2 objective functions. The optimization of this case points to minimize the springback measured through displacement measured in 20 different control points. Springback depends on several parameters. Among them are important the holding force's temporal evolution and the initial shape of the blank. Simultaneously, the height risk and superficial quality of the final piece are to be studied. It is included an operation of post-cut to the deformity to obtain the final piece in which springback measurements are performed. Design variables and objective functions used are going to show up. Some aspects of the computer team will be treated. Highlighting some of the particularities, we will talk about optimization parameters that were used and final results. This calculation has been performed with STAMPACK software, a Quantec ATZ product. The process to be optimized consists on the following stages. At first, the initial cut, in which the initial contour sheet gets defined. This contour is defined by 8 points, which positions will be controlled with 8 optimization variables. Second, the stamping process. The punch travels and deforms the sheet against the die, while blank holder applies the holding force, which value and temporal distribution will be controlled with 5 optimization variables. 3. Final cut. A cut will be performed afterwards with the shape of the final piece. 4th. Springback. Finally, there is a stage in which the piece releases the die and blank holder and gets deformed until its balanced position. To perform the optimization of the deep drawing process, 13 design variables had been used. 8 of them allowed them to change the initial sheet contour, and the rest of the variables will be used to change the holding force. 3 out of 5 of these variables allowed to determine the strength value, and the other 2 modified the application types. Through the combination of the objective functions that are already defined, we want to adjust the dimensional accuracy of the final piece by keeping the appropriate safety values. In regards of the objective functions, the first one evaluates the springback in the 20 control points. The second one will consider the piece safety to avoid it to break and wrinkles presence. The 8 design variables associated to the sheet format shown on the left shape will allow to change one of the 8 points coordinates. At the shape on the right hand side, you will find a possible geometry that you can obtain. In order to control the holding force, there were used 3 variables for the strength value and 2 for the time, as you can see on the left hand side shape, while on our right there will be different curves that can be obtained through these variables. The objective function number 1 evaluates the movement in the 20 control points. That function gives back the maximum movement value in all the square points. This way it gets minimized to the maximum instance, ensuring the rest of the values are smaller. The objective function 2 evaluates the safety. This function is minimal when the safety value is 4. That belongs to the no risk of the breakage and good superficial quality. And the rest of the not wished zones, they will be assigned values between 1 and 7. Here you will see the control points position. All of them are on the piece contour. When modifying the initial shape of the blank, it could happen that after the deformation on the cut, the piece would be too small, being this a reason to reject it. To highlight this and penalize the individual, the final area is to be checked, leaving it at 0.5% margin respecting area given as a reference. The ideal computer to perform this optimization is a regular desktop PC with an i7 processor that allows to run 8 threads at the same time. In this computer, a case or individual takes 30 minutes to calculate. The parameters informed to the optimizer are shown, highlighting that 7 threads are being used. In other words, a 7 simultaneous cases calculation is being performed. As you can see, in only 20 evaluations, around an hour and a half, utilizing 7 threads and each individual taking 30 minutes, you can get a 100% improvement in the objective function 1. At the Pareto front, graphics are shown the best individuals obtained by the optimizer. The baseline point is an initial reference case. As you can see, there will be an improvement in safety 2, F2, on the graphic that goes in detriment with the dimensional precision, F1 in the graphic. Therefore, the optimizer gives a solution family in which you will have to choose the one that suits better. Here you will see the detailed results of the 3 individuals. The best F1 is to say the less spring back, the best F2 and the more safety, and a compromise case. These are compared to the baseline. The holding force values to obtain the smaller spring back best F1 need a strength versus time curve according to the right graphic. The initial shape of the blank is obtained in a way with the shape that has a sharp break in a corner and a soft change in the lower part. In this case, we can highlight the power of the optimization method that found some hard ways to find it manually. The associated results to F1, in other words, the spring back in the control points, are shown in the chart. The minimum absolute value was highlighted in green and the maximum in yellow. At contour fill, the piece spring back is shown, which is noticeably reduced. Safety has been slightly improved. You can see that the red zones in which safety is better are increased in the upper part. For the individual that has more safety, the holding force is shown on the right hand side. There will be an increase of the initial load, just like the previous case, but downloading it later. The initial geometry is similar as shown. For this case in which the objective function prevails and is related to safety, you can see in the 20th point an important spring back. The improvements obtained in the safety are most important than the previous case, because in this case the second objective function that depends on this parameter prevails. The compromise case that has been chosen is the one marked with the blue circle. Again, the holding curve is pretty similar to the others. Same as the initial format, it is similar as well. The spring values of the points are in general very good, except the point 20 located at the corner that has a higher displacement. At safety, you can see that it improved too in different areas. At the chart is shown a comparative summary of the designated individuals like baseline best springback that is improved in some cases, best safety that is improved in all the cases, and compromise. The compromise solution offers a balance between both objective functions. Thanks for your attention. If you wish more information, you can contact the Cimne RMOP team to the following email address: metalform@cimne.upc.edu or visiting our webpage at tts.cimne.com/rmop.